And today we're doing like graphing cosine and stuff like that.
Okay. It sounds like maybe you're working on the sinusoid function,
Mm-hmm.
which is is this the way they give it to you? As the
Yeah.
format? Is it exactly like this? Because there's actually 3 different general formats.
Yeah, that's the way they give it.
Okay, good. That's the one we'll work with. Okay, what do you got specifically?
Okay, so the first problem is y equals -2 secant 1/2 x.
That it?
Yep.
Okay. So let's start with the sinusoid function. What is A?
-2.
What is B?
1/2.
What's C?
0.
And D.
0.
Okay. So what? And you're supposed to graph these, right?
Yep.
What's the A equal minus? A is actually equal to 2. A is the absolute value of that.
Okay, yeah.
The negative sign means what?
You're supposed to start down.
It's a reflection across the x-axis. Okay? So, if I was going to draw, let's just draw the secant curve. A normal secant curve would be the inverse of the cosine, which means it sits on tops and bottoms of the cosine curve. You with me?
Yep.
The fact that it's a -2 means that it's going to be reflected like that instead of the first thing I drew.
Okay.
And let me draw all these in a different color so you'll know. In other words, this is y equals secant x. This is y equal -secant x. And I've only drawn one period of it. There is another period, which would go basically up here. In other words, the blue graph, top and bottom, is y equal -secant x. You with me?
Yep.
You know why there's 2? There's top and bottom. Okay, now we got to figure out what to do with this b equals 1/2. Well, there's a translation to be made here. What is b in terms of the period? This is the one equation that you have to memorize right there.
Okay.
Okay? So I need to figure out the period. I know what b is. B is 1/2. What's the period? In other words, if b is 2 pi over the period, then also the period is 2 pi over b. With me?
Yeah.
So what's the period going to be?
4 pi.
Correct. And what that means is that everything gets wider.
Okay.
Let me make some space here. hate to erase that equation because that's the most important one. But so normally this would go from minus pi over 2 to pi over 2. And the secant would look like this. Okay?
Okay.
But we know its period is twice. So we know it's actually going to be expanded horizontally. Well, rather than expanded horizontally, let me just do this. Let's make this from minus pi to plus pi. Does the same thing. You see why?
Yeah.
Okay. And now I do want, now this is y equals secant of 1/2 x. That's all it is. And
Okay.
the rest of it would be like that. Well, we're dealing with y equals -2 secant of 1/2 x. And the only thing that -2 does is it reflects it and it changes the amplitude. So if I want, I can reflect it. That's it reflected. You with me?
Yep.
And changing the amplitude makes that go from 2 to -2 instead of from 1 to -1. So the red curve is the correct answer.
Okay.
I may not have drawn it exactly appropriately, but that's the way you do these sinusoid functions. They really are an awful lot like transformations of polynomials. In fact, there is virtually no difference. This is a vertical stretch factor. This is a horizontal stretch factor. This is a horizontal shift, and that's a vertical shift.
Yeah.
For some reason, Trig insists upon teaching it differently. They really do not constantly refer to transformations, and yet be much easier to understand for the student if they did. But that's basically what you're looking at. All right, what else you got?
Okay, the next one is y equals 2 plus cotangent, and then in parentheses 2x minus pi over 3.
All right. This is significant. This got a couple of things with it. What's the 2 out in front going to be?
The vertical shift.
Yeah. So I really should write this like this. Now it's closer to our general format. What's B?
Pi over 6.
Well, you're close. You got the right idea. The real key question is in your general format, is the B in front of the parentheses or inside the parentheses?
Inside.
It's actually outside. Well, I don't know for sure. It depends on what your school does. Do you have a book that lists this because there's 3 different ways to do the general formula. You can put the b outside, you can put it inside, or you can also use a plus c instead of a minus c. And they're liable to give it to you in both ways. Notice that the way they gave you this, the b is inside.
Yeah.
Well, we don't want the b to be inside. Because when the b is inside, then c is no longer the horizontal shift.
Yeah.
If the b is outside, then c is the horizontal shift, or what they call phase shift. So let's take the 2 out.
Okay.
Easy enough to do. What should that second part be? If I'm factoring 2 out of that from inside the parentheses, what's the pi over 3 become?
Pi over 6.
Now that's the phase shift.
Yeah.
No longer have any doubts as to what everything is.
Mm-hmm.
B is 2, the phase shift is positive pi over 6, and plus 2 is the vertical shift. Okay? So I'm going to draw 3 different curves here. First of all, cotangent typically goes from 0 to pi. There's a horizontal or vertical asymptote there, and it's always decreasing function. Looks a lot like negative tangent.
Yeah.
Only difference is negative tangent would go from minus pi over 2 to plus pi over 2.
Mm-hmm.
Okay. Now, in blue, let's deal with this 2. What does that 2 do? That's b. What's b equal to with tangent and cotangent? It's actually different than sine and cosine. With tangent and cotangent, the natural period is pi. It's not 2 pi. Notice that 1 complete period of my cotangent curve goes from 0 to pi.
Mm-hmm.
If I were to draw another one, another period of it would look like this. But that's a second period. It's not the other half of the first period.
Okay.
Okay? So, if I'm going to use this formula, well, I know the period is equal to pi over b, and I know b is 2. So the period is pi over 2 in our case.
Mm-hmm.
So instead of going from 0 to pi, I'm going to let it go from 0 to pi over 2. I'm going to put my vertical asymptote there, and cotangent's going to go like this, with that point being pi over 4 comma 0.
Mm-hmm.
Now, we got 2 other things we have to concern ourselves with. This and this. Let's take the phase shift first. What does that do?
Shifts it pi over 6, right?
Okay. So I'm taking this middle curve, and I'm just going to move it to the right by pi over 6. So let's see, if that's pi over 2, then pi over 6 would be about 1/3 of that way. So this is where my first vertical asymptote goes. Where's my second vertical asymptote go? It's over here somewhere. It needs to be shifted pi over 6 to the right also.
Okay.
So what's pi over 2 plus pi over 6?
2 pi over 3.
Yeah, it's 3 pi over 6 plus pi over 6, which is 4 pi over 6, which is 2 pi over 3. So this point, 2 pi over 3, this point, pi over 6. Now I'm going to draw my tangent curve normal, and this is y equals cotangent of, I'm taking the 2 out, x minus pi over 6. With me, we're going to do these one step at a time.
Okay.
The last step is applying that plus 2. What's that plus 2 do?
Shifts it up or down.
In this case, up. So I find myself a point. I know where that point is. The blue point. That's halfway between pi over 6 and 2 pi over 3.
Yep.
And it's on the x-axis. So I'm going to move that point up 2 units.
Okay.
And I'm going to draw everything through that point. So basically my blue curve tends to be parallel to the red curve in the lower right. And that's the way you always do these, is you find a known point and you just shift it vertically up or down by whatever this is. And then you draw your normal looking curve. So my normal looking curve is going to go from minus pi over 6 to 4 pi over 6. It's going to go always decreasing. That's what cotangent does. And the whole curve is going to be shift up 2 units without changing its shape.
Yep.
Now, the horizontal compression that happened, in other words, when I did this part, that did change its shape. When you compress, when you stretch or shift, that changes shape. When you do a horizontal shift or a vertical shift, it does not change shape. It's only with vertical stretches or horizontal stretches that you change the shape of the curve. Notice what happened to it is it became skinnier.
Yeah.
Vertically stretched, which is the same as horizontally compressed. Always realize that, is that this curve right here is horizontally compressed, but if I was just looking at it, I couldn't tell the difference between horizontal compression and vertical stretching.
Okay.
So this curve only reflects the new period. This curve over here reflects the phase shift and the amplitude. And that amplitude also, oh no, there is that, no, excuse me, that's not an amplitude. That's strictly affecting the period, and this is a vertical shift. So there is no amplitude stretch here.
Okay.
Okay. This time I'll try to draw stuff smaller so that we can go through it one step at a time. But I definitely recommend you always go through these one step at a time when you're drawing them.
Yeah.
Because you really can't make a mistake if you do it that way. If you try to do all 3 transformations at once, you can end up making a mistake pretty easily. What else you got?
Okay, so the next one is y equals 1/2 cosecant, and then in parentheses x minus pi over 2.
Well, your teacher doesn't like giving you the easy ones, does he?
No.
All right. Turns out that really the very first thing you should do is this one right there when you're graphing it. Okay? First of all, let's graph cosecant of x. Where's that go from?
So it's to the right, pi over 2.
Let's first graph it without the phase shift.
Okay.
So what's cosecant of x look like all by itself? Sits on top and bottoms of which curve?
Of sine.
Okay. Which puts it right here.
Yep.
That being -1, that being +1, that being pi, that being
Okay.
2 pi. You can see the natural period is 2 pi. In other words, the natural period encompasses both the top and the bottom before it starts again. You do also have asymptotes, always. Wherever sine and cosine can be 0, you know you're going to have an asymptote because when you do the reciprocal, you're dividing by 0. Okay? So this curve right here is y equal cosecant of x.
Okay.
Now, over here, what's the period of this curve? The first one?
4 pi?
It's 2 pi.
Oh, yeah, it's 1/2. Yeah.
Okay? Well, no, it's not 1/2 yet. We haven't applied that amplitude yet.
Oh.
Okay? In other words, I'm doing this one step at a time. Let's start with the parent function, how we graph y equals cosecant x.
Okay.
Okay? That's what I've graphed. Now, in blue, let's graph y equal cosecant of x minus pi over 2. What's the first thing I do? A minus pi over 2 is what? It's a phase shift in which direction?
Right.
Okay. So I'm going to take this asymptote that was there. In fact, I'm going to take all my asymptotes and move them pi over 2 to the right.
Oh, okay.
That's going to be pi over 2. And that's where my first vertical asymptote goes.
Okay.
What's the period?
2 pi.
So my last vertical asymptote goes where? My last one, I mean the last one if I'm only plotting one period. Add pi over 2 to 2 pi. What do you get?
5 pi over 2.
Notice that that is still a period of 2 pi.
Mm-hmm.
The period has not changed. We do have another vertical asymptote. Goes right down the middle. What's that at?
3 pi over 2.
Yeah, you want to learn to quarter these up. A very important process in graphing sinusoid functions is to figure out what the period is and then to quarter it. By quartering it, I've quartered it. I got the beginning, the end, and the middle. I could also use a point there and a point there. Fully quartered. Okay.
Okay.
Now, this thing goes like this. In other words, if I'm graphing cosecant of x minus pi over 2, it's going to look just like this.
Okay.
That's not what I'm graphing, though. I'm graphing half of that.
Oh.
So what's my final curve look like? In other words, let's do the whole thing now. How do I change it? What's that 1/2? Is it a vertical stretch or a vertical shrink?
Vertical stretch.
Shrink. When it's less than 1, it's a shrink. When it's greater than 1, it's a stretch.
Okay.
So less than 1 means I got to get down to that point.
Yeah.
And the other side of it, in other words, this point becomes minus 1/2. This point becomes plus 1/2. There is one period of my curve. Only one. In other words, if I wanted to draw the whole thing, I would draw more over here. There's another half period. And then more up there. There's another half period.
Yeah.
But there would be 2 complete periods of 1/2 cosecant of x minus pi over 2. And there are 6 possible transformations they can throw at you. That's it. And you can do, even if they give you one that's got all 6, you can do them one at a time. Let's say I have this. There are 5 transformations. I won't do the 6th one because it kind of tends to confuse. But whenever you're doing a phase shift, it's best to figure out what your period is and start with the phase shift.
Okay.
So let's say I'm doing this one. What's my period? It's hard to go wrong by starting off with period.
2 pi over 3.
Good. So if I'm going to graph this thing, minus pi over 4 is a phase shift in which direction?
To the right.
Okay, so I'm going to go to pi over 4. And then I'm going to add 2 pi over 3 for 1 full period. So pi over 4 plus 2 pi over 3 is 3 pi over 12 plus 8 pi over 12. That's 11 pi over 12. So that needs to be 11 pi over 12 past pi over 4. No, it doesn't. Excuse me. That is 11 pi over 12 right there. In other words, I already did that.
Yeah.
So, and this is the sine curve. So I'm not going to draw any dotted lines because there aren't any vertical asymptotes. But basically what I'm going to do is I'm going to quarter that up. And then I'm going to draw the sine curve the way I normally would. Sine curve starts there, goes up to its high point there, goes down to its low point there. Let me just draw a modified version of this function. So this would be sine of 3x minus pi over 4. In other words, I've incorporated the period, the 3 changes the period, and the pi over 4 changes the phase shift. But the best way to do it, I used to do it a different way. I used to draw everything without the phase shift, and then I would just take my answer and shift it. So I would have a curve that was parallel to it.
Okay.
But turns out that's not really the best way to do it. The best way to do it is to figure out your period, figure out your starting point, and then add 2 pi over 3 to pi over 4 to figure out your ending point.
Okay.
once you have a starting point and an ending point, you can quarter it up, and then you can draw your curve, your regular sine curve that starts at your starting point, comes back to that starting point.
Okay.
Okay. Now, to do the rest of it, well, that -2 is a reflection and an amplitude. So immediately, if I do the reflection and then the amplitude, looks something like that. You with me?
Yeah.
Now this is almost done. The only thing I have to do is that. What does that do?
Vertical shift of 5.
Yeah. So I'm going to go up to 5, and I'm going to start the curve right there. And so it's going to look something like this. In other words, the new horizontal line of symmetry is at y = 5. But that's pretty much the way you handle graphing sinusoid functions. And as you've already learned, it doesn't have to be a sine to be a sinusoid function. It could be sine, cosine, tangent, cosecant, anything. But it operates pretty much on the same principle as transformations do.
Okay.
I thought I found a difference last time I had a student and I was looking at it. I've never been able to figure out why they don't just call them transformations. Because they don't. They change the name. They call this amplitude. They call this the period adjustment. They call that phase shift. And then they do call that vertical shift. But that's about the only one they call the same. Well, they should call them all the same. Then they wouldn't confuse students. That's a vertical shift. That's a reflection. That is a horizontal stretch. Excuse me, that's a vertical stretch. That's a horizontal shrink. That is a horizontal shift. And that is a vertical shift.
Yeah.
And that's really the way to look at it. And like all functions, you want to do your reflections first, always.
Okay.
Anything that's got a negative sign. The only one I left out here was putting a negative sign in front of the x, which is quite a bit trickier. There's a way to do it, but you kind of have to write this way. If I were going to do that, I would use double parens like that. And now this negative sign is a reflection over the y-axis, and that's the phase shift. Pi/4 to the left.
Oh, okay.
So when you have a negative sign inside the parentheses, you kind of almost have to use double parentheses if you're going to do a phase shift. It gets a little complicated. It's the same principle as if I had this. Okay. That negative sign is a reflection over the y-axis, but only after I rewrite it. I have to rewrite it like this. Now it's the e to the x curve, reflected over the y-axis, shifted 3 units to the right. Well,
okay.
The e to the x curve, reflected over the y-axis, is like that. Shifted 3 units to the right. This point right there goes to there. It's like that.
Oh, okay.
So it's a little tricky when you have that negative sign inside the function. You have to make sure that that horizontal shift is correct. In other words, you see where that is the same as this. Exactly the same. If you remove the parentheses, you have minus x plus 3. So when you add the parentheses, you have to sometimes change the sign on that.
Okay.
Okay? And it doesn't matter whether it's a polynomial or a trig function, same principle.
Okay.
All right. Ved, I will talk to you next time.
Yep, thank you.
You're welcome. Bye-bye.